began in minutes. Proton storms cause all kinds of problems. They interfere with ham radio communications. They zap satellites, causing short circuits and computer reboots. Worst of all, they can penetrate the skin of spacesuits and make astronauts feel sick. An astronaut on the moon, caught outdoors on January 20th, would have had almost no time to dash for shelter, says Lynn. The storm came fast and hard, with proton energies exceeding 100 million electron volts. These are the kind of high-energy particles that can do damage to human cells and tissue. The last time we saw a storm like this was in February 1956, Lynn says. The details of that event are uncertain, though, because it happened before the space age. There were no satellites watching the sun. According to space weather theory, soon to be revised, this is how a proton storm develops. It begins with an explosion, usually above a sunspot. Sunspots are places where strong magnetic fields poke through the surface of the sun. For reasons no one completely understands, these fields can become unstable and explode, unleashing as much energy as 10 billion hydrogen bombs. From Earth, we see a flash of light in X-rays. This is the solar flare, and it's the first sign that an explosion has occurred. Light from the flare reaches Earth in only 8 minutes. Next, if the explosion is powerful enough, a billion-ton cloud of gas billows away from the blast site. This is the coronal mass ejection, or CME. CMEs are relatively slow. Even the fastest ones, traveling 1 to 2,000 kilometers per second, take a day or so to reach Earth. You know a CME has just arrived when you see auroras in the sky. En route to Earth, CMEs plow through a lot of gaseous material, first in the sun's atmosphere, and then out in interplanetary space. You thought space was empty? No. The void between planets is filled with protons and other particles from the solar wind. Shock waves in front of the CME can accelerate these protons in our direction, hence the proton storm. CMEs can account for most proton storms, says Lynn, but not the proton storm of January 20th. According to theory, CMEs can't push material to Earth quickly enough. Back to the drawing board. If a CME didn't accelerate the protons, what did? We have an important clue, says Lynn. When the explosion occurred, sunspot 720 was located at a special place on the sun, 60 degrees west solar longitude. This means the sunspot was magnetically connected to Earth. He explains, the sun's magnetic field spirals out into the solar system like water from a lawn sprinkler. Why? Because the sun spins like a lawn sprinkler does. The magnetic field emerging from solar longitude 60 degrees west bends around and intersects Earth. Protons are guided by magnetic force fields, so on January 20th, there was a superhighway for protons leading all the way from sunspot 720 to our planet. That's how the protons got here, speculates Lynn. How they were accelerated, however, remains a mystery. What does all this mean for astronauts? Stay inside when there's a big sunspot located near solar longitude, 60 degrees west. Or, if you must go moonwalking, take a radiation shelter with you. It's not as hard as it sounds. Stay tuned for more on this topic in an upcoming Science at NASA story. Radiation shelters. Don't leave home without one. This story was written and read by Tony Phillips and presented by Science at NASA. To find more Science at NASA stories on the Internet, please visit science.nasa.gov.